Good afternoon, and welcome to the fourth of our six-part speaker series. I'm Dave Cancam, the University Affairs Officer at NASA Glenn Research Center in Cleveland, Ohio. Today's talk, Power Energy Storage and Conversion, is very pertinent to the key aspects of the design challenge. I think we're also particularly delighted to have one of my long-standing colleagues, Dr. Rodger Dyson, to speak today on that topic. Dr. Dyson is the lead for hybrid gas electric propulsion here at NASA Glenn Research Center. Additionally, he's also the element lead for NASA Electric Aircraft Testbed, or NEAT. In addition to that, he serves as the Chief Technology Officer and Vice President of Technology at Nirvana Energy Systems. And that's not all. He also has commercialized engine technology for UAV market sector. He's a very busy young man. Dr. Dyson holds a bachelor's degree in physics, mathematics, and computer science from Hiram College, as well as a PhD from Case Western Reserve University here in Cleveland. He's a holder of 3 patents plus 4 others pending. And he also serves outside NASA as an adjunct graduate faculty member at Cleveland State University. So as you say, we're very fortunate today to have Dr. Dyson speak on the topic at hand. And I'll call him at this time to make his presentation to all of us. Thank you.
Well, thanks, Dave. This is a great opportunity to share some of the exciting work that we're doing here at NASA Glenn. And I think you'll find that it's very apropos for the design challenge that you're faced with. It's a very exciting area, hybrid electric aircraft overall. It's enabling technology, enables new commercial markets, fuel savings, emission savings, number of benefits. So I'm going to go through and discuss a range of technologies that are useful for this area and this application area. And like I said, at our center, it's a new and growing area as well. So with that, let's get started. Okay, so power, energy storage, and conversion for aircraft. Power refers to the generation of power. Energy storage is obvious, and then conversion is maybe not so obvious, but converting from heat to electric, converting from different forms of energy actually are all required to have a net system that has a net benefit. Okay, so first I'm going to go through and give you a primer on electric aircraft, what we talk about, what we mean. Why electric? So obviously emissions is a big deal. Less atmospheric heat release to minimize effects on the environment. Quieter flight. The technology enables an opportunity to reduce the noise. Better energy conservation, and we can also result in more reliable systems because of different layers of redundancy you can build in the system, and especially for your design challenge involving people, it's going to be very, very important that you comply with FAA regulations and create a safe environment for people. You're going to be flying in busy areas. There's already been a lot of success that's been achieved with the all-electric general aviation aircraft. And as you know, with UAVs, there's an ever-growing demand for that, and it's anticipated in the next couple of years, FAA is going to modify the regulations so we can have more product deliveries, and it's just a exciting, growing area. We've also at NASA have done some advanced concept studies over the past couple of years, looking not just at the UAV range, but all the way up to full-scale large energy transport aircraft. And industry is very much developing. You've probably recently heard of Uber interested in fact, they hired one of our colleagues recently to develop taxi services and on-demand mobility, which is again related to your design challenge. And then the pictures you're seeing there in the middle, I think I have the ability to do this. Yeah, so that aircraft in the middle is what we think is going to be over the next 7 or 8 years a focus of a lot of attention, and a lot of this presentation will kind of explain why that is. But it's a Boeing 737 with a ducted propulsor on the tail. And then on the right there is N3X, so a 30 years from now aircraft that holds 300 people and is much more efficient than today's. So that's kind of the range of what we're researching here at NASA Glenn. Electric vehicles actually have been under development for a number of years in other sectors. So submarines, the Navy, automobiles. You're familiar with hybrid electric automobiles. You can kind of see the RPM increases as you go to the higher powers for these electric motors. But what's new is aircraft have not only the requirements of these other technology spaces, but they need to be flight weight and they need to be efficient. So we're talking like 99% efficient and 3 times lighter than today's technology in order to have it be a net benefit. Again, trains and other objects, you're not so concerned about the weight. Aircraft, very much. You might be 99% efficient, but if you just doubled the weight of the aircraft, you're still going to use more fuel than you would have otherwise. So it's a net loss. So there's really 2 paths as we see it with electrified vehicle configurations. There's the all and hybrid electric distributed propulsion, which fits your design challenge of on-demand mobility and also small plane focused. That really is technology that's uses more electric, rather than turbo machinery. Rather than using jet fuel, you're using really more energy storage. And the reason for that is you can only store so much in a battery or in a supercapacitor, and so it limits your mission duration, or it limits the size of the vehicle that you can work with. So, like for example, in your design challenge, you were given the opportunity to suggest that the battery and supercapacitor had a lot more storage capacity than what you have today. You actually need that in order to have the system closed, so that's why that was offered to you. On the other hand, if you have larger vehicles, 150 passenger, 300 passenger, typical commercial transport aircrafts, you need more than just battery storage. You actually need to generate the power on your aircraft, and you still have batteries, but you're actually generating the power on the vehicle as well. But you're still using electric motors and components, which gets you, 10 to 20% fuel savings and other benefits. So when you look at the motivation for electrified aircraft propulsion, there's a chart here on the page where I'm circling right now in the green. You can see that most of the fuel that's consumed in the aviation community is actually by large aircraft. And so we focus most of our research at NASA Glenn on that, so you can have the largest impact. You can see that the smaller vehicles are perhaps require less power, but they're also don't have as large of a footprint in terms of the fuel usage. You can see in the chart over here where we compare a turboprop versus a turbofan versus a battery versus a fuel cell. And you can kind of see all the different trades that go into it. When we talk about efficiency of a vehicle, it's not just the efficiency of one component. It's the whole powertrain efficiency. So when you look at the whole powertrain efficiency, for example, with batteries, you might conclude that you're 73% efficient potentially, but if you actually look at the full cost of producing electricity, since you produce electricity today with coal or natural gas or other sources predominantly, if you look at today's grid and today's situation, you end up with roughly between 30 and 13% net efficiency is what you actually achieve. So it's important to look at the full cycle. And the same thing with this Stark-Able vehicle that I'm showing you here. We call it Stark-Able. It's an acronym, single turboelectric aircraft aft boundary layer vehicle. And essentially, this vehicle, there's a component in the tail that is it's a 3,500 horsepower electric motor that reduces the fuel usage of the whole vehicle by about 10%. So you can see that by just doing a slight modification to this Boeing 737 vehicle, you can actually save about 10% of the fuel. And you can see that compared to the turboprops, turbofans, battery, and fuel cell, that's a pretty substantial change and an improvement for fairly minor change to the vehicle. So again, we see fuel savings, noise reduction, carbon and NOx reduction, as well as new mission usage, so mobility and safety. So in your case, the on-demand mobility is very much enabled by this electric aircraft technology. So talk about the grid a little bit. And especially for your on-demand mobility, you're going to be relying on the grid to charge up your batteries, or supercapacitors. Today's grid is roughly 30% efficient. So if you're using any of your systems or taking power off the grid, you're already starting at only about 30% efficient. Now in the future, with combined cycle power generation plants, the future grid's going to be over 60% efficient. That's going to take a number of decades to get to that point as we move forward. And I'm showing here actually a potential superconducting power grid in the future, where you can get even higher than the 60% efficiencies. But there's a lot of technologies which we are working here at NASA Glenn actually at this time, and other groups are as well. But that's a 20 to 30 year out time frame before we can kind of count on superconducting to help us. So here's why fossil fuels have been needed up till now. I'm showing the Stark-Able video, and I'm also showing the a UAV video. And here we see a battery-powered Boeing 737. The battery would need to be so large that it would add too much weight, and that can't work. So and that's because if you look at these energy densities down here, coal, wood, oil, natural gas can provide a lot more energy storage per weight than batteries can. So for example, you can see a lithium battery is 50 to 100 times less energy storage than what you would get from jet fuel today. So that's a lot to compensate for. So what we're doing is hybrid. Hybrid means that you love to use all electric. You love to have 100% efficient grid. You love to have it all be solar or renewable. But you also want to make progress with where we are at today. And so with where we're at today, hybrid is kind of your transition point to improve your fuel efficiency without going completely electric. And again, it boils down to this energy density problem and mission duration challenge. Now, fortunately, UAVs today, if they're in the 55-pound class, batteries are working. You can get an hour's worth of flight roughly out of them. But in the future, you like to do better than that. So electrified aircraft propulsion development actually has a number of different players. I already talked about the electrical energy production and distribution, roughly 30% efficient today. You've also got the energy storage component. You also have to do the integrated designs, which you're working on for your design challenge. You also have the system testing and evaluation part of it. You also, if this is going to be actually used by people and actually commercially viable and it makes a difference in people's lives, it's got to be certified, which means the FAA says that it's safe to use. And then you also have to have it be affordable for the end user and buyer. So there's a lot of different players, a lot of different government agencies and companies that are all involved in making the whole ecosystem work. It's exciting, and I can say that all these different groups are actively working it. So even though it's a big challenge, there's a big payoff. Okay, so now I'm going to talk about the powertrain architecture a little bit, and start talking about some of the options for for on-demand mobility as well as the large transport. Okay, so what challenges are there? Well, we are developing an all-electric flight demo that's actually going to be flying in 2018. We are developing a full-scale powertrain testbed, and we're also working some of the certification standards. In addition, some of the challenges are if you have in the case of your design challenge, many thousands of vehicles flying through cities, you've got to manage the air traffic control of those. You do need to show a net benefit of greater than 10% typically for the commercial sector to accept it. And we have identified the key performance parameters that are required to get a net benefit. In other words, given today's electric motors, today's power electronics, how much better do they need to be in terms of efficiency and mass to be able to be used in aircraft or UAVs in a way that would be acceptable to the community. And there's other challenges. Fault management. As you increase the power levels in higher voltages, you have real safety issues, both to the vehicle and to people. And you're increasing the load density in congested urban areas. There's cost pressures, and there's technical and economic loading schedules that have to be addressed. So there's a lot of different ecosystem challenges that need to be addressed, and we are working on them. So how are we tackling that right now? Well, what I'm showing on this chart is a range of vehicle classes going from general aviation all the way up to full-scale transport aircraft. And what you can see is that the power level required grows up to 30 megawatts. Okay, so that's pretty significant. The Boeing 787, for example, that actually has about a megawatt of power available to it, and it's what's called a more electric aircraft. But it does everything but propulsion. So there are no electric propulsion systems on the Boeing 787. But everything else they've tried to make electric because you save on maintenance by getting rid of hydraulic systems, by minimizing the different kinds of systems so that they're all based on electrical components. It's easier to maintain. So the next step is electric propulsion. And once you start talking about electric propulsion, turbofan engines have a lot of power in them. And it's very difficult to do that with electric motors. And so if you would have used electric motors from just a couple of years ago, they were the size of a bus to get 10 megawatts. Now they're used in factories all the time. 10 megawatts is nothing unusual, but making them very efficient and very lightweight and small enough to fit on an aircraft, now that's a whole new challenge. So what I'm going to show here is if you look at my line at the 1 megawatt scale, you can see that almost all of the aircraft, whether it's the small aircraft or the large aircraft, all have a component that needs a megawatt level electric motor and power electronics. So a lot of our research is actually in that circle. So you'll see a lot of the work we're doing is actually focusing on the 1 megawatt with the idea that you could scale down or scale up from there. But 1 megawatt is kind of the key research point. And for your on-demand mobility, that's actually not unreasonable depending on the number of passengers you're going to take. A 1 megawatt system could very well be what's needed. Okay, and so now I have a short video.
How do you see the future of flight? What's the shape of things to come? How might jetliners be designed and powered? Not just a few years from now, but decades. These are some of the questions that NASA asked a Boeing-led team to examine.
There was a time at a conference on advanced aircraft technologies where somebody stood up and said, "What about electric airplanes?" And everybody laughed. And that was only about 5 years ago. So we sort of took that as a challenge. Can we make an airplane that has electric motors and batteries actually work?
After looking at hundreds of ideas, one concept emerged as potentially viable and desirable. The team calls it Sugar Volt.
Sugar Volt is really similar to what people do with hybrid electric cars. We have an engine that will operate on a combination of electrical power or conventional jet fuel. So it plugs in at the airport, charges its batteries up, flies its mission.
Sugar stands for Subsonic Ultra-Green Aircraft Research. Volt suggests that it would be driven, at least in part, by electricity. The Sugar Volt concept has twin engines that burn fuel in each engine's core when great power is needed, such as takeoffs. Then, to enable portions of the flight to be made with lower or even zero emissions, it would use electricity to supplement or even replace power to the turbofans.
Well, we're looking out to the 2030 to 2050 timeframe. The goals that we're working to in the Sugar study are to reduce the amount of fuel burn by approximately 70% compared to what airplanes do today. And along with that, also be quieter and reduce the environmental impact of air transportation.
The Sugar Volt's long wings are designed for greater lift and less drag, so the aircraft would not only be more fuel efficient, it would have shorter takeoffs and generate less noise. To save space on the ground, the wings would also be designed to fold, allowing use of the same airport gates that exist today.
The Sugarbolt airplane combines a whole suite of technologies together. It includes advanced aerodynamics. It has a better wing. It has a higher span wing that's more efficient. It has better propulsion. But what the Sugarbolt adds is it adds a hybrid electric approach. We're defining the future of commercial air transportation.
All right. And that's called the Sugar Volt. There's also something called the Sugar Freeze, if you wanted to look that up afterwards. The Sugar Freeze looks an awful lot like the Stark Able that I showed you earlier, in which you have a tail cone thruster added. So that came a little bit later. All right. So this is the Stark Able configuration and the Sugar Freeze, if you look that up, in which we take some of the power off of the turbofans, between 10 and 25% of the power. So we're still producing thrust, and so we clear what we're talking about. So we have thrust coming out of here, and we also have electrical power coming out of those locations, traveling along these DC bus cables to an electric motor, and we also have thrust back here. And this rear thrust, actually what it's doing is, normally you'd have a wake that's formed back here, just like in the back of a boat. And so what we do is, by energizing the flow in the back, we're filling that wake so we don't have a pressure drag. So even with your on-demand mobility design challenge, you could save some fuel by using a similar concept of removing the wakes. But the point of this is showing that the total system weight very much depends on the overall voltage that you're using. So, for example, we believe that 2400 volts is going to be the optimal for this size of an aircraft. While you get a little bit of benefit if you go to higher voltage, it starts becoming more difficult, and there's a lot of issues with the Passions curve as you go to higher altitude. Makes it more difficult on the insulation and other properties when you go to these higher voltages. So that's where we're at. For your design challenge, you're probably not going to go as high in altitude, so you could probably go to a little higher voltage than that. But again, this is the concept that we think is most attractive at this time. It gets you a 7 to 12% fuel burn, and it doesn't require significant changes to today's aircraft. So we're very serious about having this kind of technology be implemented by keeping it in a regime that people will accept in the short term. So what technologies are required? So we need better electric machines. We need better power grids, especially at the higher power level. We need better materials and subcomponents to develop these electric machines and power systems. And we need better energy storage options as well. And especially if you're going for the on-demand mobility using batteries and supercapacitors and no onboard power generation, it becomes very critical. When you run the system studies, there's very much a need for energy density on aircraft. So system level studies and tests are required to pin down all of the parameters for each of these different technologies. And in the past year and a half, we have identified for the single aisle transport aircraft what those are. Now, in the UAV community, there's still it's still a lot wider open as far as what your options are. There's some people that are looking at cryogenic hydrogen fueled fuel cell UAVs. There's the battery community, supercapacitor community. Depends on your mission profile. Some people are developing 72-hour weather based UAVs. Package delivery under 55 pounds is another class. Your design challenge is somewhere in between there. But there's a wide range of technologies, and I think it's fair to say that the energy storage path, all electric path, is certainly reasonable for the smaller vehicles, but you're heading towards the turbofan, turbo generation scale when you get above 100 passenger vehicles. Okay, so here's showing a trade space of what you can trade. You can trade, for example, the percent of the propulsive power that comes from electrical energy storage. You can also trade the amount of power that's coming from your turbo generation. That's why it's hybrid. You're using partially stored energy or partially turbo generated energy. And then there's this kind of catch-all phrase here, what we call propulsion airframe integration. And that's where a lot of the magic happens. The propulsion airframe integration that's an example of when we eliminate that wake in that Stark-able aircraft. You're actually changing the aerodynamics of the vehicle itself. If you didn't do that, if all you did was you took power from one part of the aircraft and moved it to another, you actually would have a net loss, because anytime you convert power from one form to another, there's an efficiency loss associated with that. Typically 10, 25% or more when you look at the full system loss. But because of that, the freedom of being able to locate that that ducted fan in the rear, where the incoming boundary layer is not ideal for turbofan engines, electric motors are fine. They're not so concerned about that incoming boundary layer, and so you're able to get a 10 to 12% net benefit, even though by using the turbo generation from the turbofans, let's say the generators are 97% efficient, power electronics might be 97% efficient. The distribution system, by the time you look at the whole system, you're losing 10% or more of the energy. So you need to have some way to regain, to even get a net benefit. And so that's what this distributed propulsion allows, is you can put these propulsors in different places on the aircraft. So propulsion airframe integration could be a tail cone thruster, like I was showing. Could also mean putting additional propulsors on the wing. Some people are working that issue, where by increasing the number of propulsors across the wing, you're effectively increasing the bypass ratio of the turbofans. You're also increasing the wing lift, because you're having higher velocity airflow over the wing. So there's a lot of those different situations. So the same thing for your design challenge. There's going to be interesting architectures that are possible because you're not constrained to a jet-fueled configuration. Okay. So what are some near-term options? Well, there's really the two near-term options are the parallel hybrid and the turbo electric. Now, the parallel hybrid is what that video that we just showed from Boeing, that's that sugar concept, in which they're actually putting the electric motor on the same shaft as the turbofan. Okay, so the turbofan has jet fuel going into it, and it has torque from the electric motor. So both of those energy sources are turning the same fan shaft. All right. Now, in the case of turbo electric, we break that up. We have the jet fuel still providing power into your turbo shaft, but now the propulsion is strictly electric. Okay, so we have these electric motors that are getting its power from this generator. All right, and that's the Stark-able concept, where we're using this rear tail cone thruster by taking the power off of the turbofan here and the turbofan here. So these are seen as short-term, and in the aircraft industry field, short-term is 10 years. I mean, typically it's 20 years or more to introduce technologies, into the marketplace. So research might be seen as 30 years out. But this is much more short-term, with an eye towards making an impact as soon as possible. Okay, so now we're going to talk about some of the powertrain technology options.
Coster, just a question.
Oh, sure.
Question from Brennan Barrington says, could a tail cone thruster be used on a lighter than air vehicle for even greater drag reduction, since pressure drag dominates on an airship?
Yes. Anytime you're filling a drag or deficit area with excited air, yes. But again, you have to look at how much mass you're adding to the vehicle by doing that, because there are going to be compromises and structural things you need to do differently. So if you're not adding a lot of weight, and also the efficiency matters, because a lot of these vehicles, close to 50% of their mass is fuel. So so if you actually added that tail cone thruster but did it with an inefficient process, maybe you've eliminated some of the drag of the vehicle, but now you've added weight to the vehicle, which adds more to your drag. So, it really is a systems analysis. So the answer is yes, but you have to do your systems analysis to confirm that you get a net benefit. Okay, so we're going to talk about some of the core technologies, which include solar power generation, batteries, fuel cells, regenerative fuel cells, flywheels, thermal energy conversion, where you convert from, like for example, heat to electrical power, heat rejection, and power electronics. All of these components need to be developed to support the full flight weight system benefit that I've been talking about. So, for example, I'm showing it'd be great to have a solar-powered plane. Okay, in fact, they've done that. All right, but if you use solar power exclusively, which you can do, and they have flown, but there's only so much energy available in that system. And plus you're adding weight from the fuel cell and the power conditioning system, and you got your electric motor and so forth. So all of those things are adding weight to the vehicle, and you have to look at the weight versus how much energy and power is available. So some of the areas that need to be addressed include the system conceptual design. It includes the integrated subsystems, so the flight controls of all this very much matters. NASA's working that as well. We need to have power-dense electric machines, power-dense power electronics, which means higher voltages than have been done in the past. And we need interesting materials, especially insulation, for example, because as you go to higher voltages, you need new kinds of insulation. As motors get smaller and power electronics get smaller, you run into the situation where, if you're familiar with Passion's curve, if not, you can look it up. But essentially, if you have two electrodes, as they get closer and closer together, they will tend to spark at a particular voltage, and that voltage decreases as you go up in altitude as the air gets thinner. So so the insulation requirements, as you increase the voltage and increase the altitude, become more challenging. Okay, so some of the technology paths that we are actively working are this ambient temperature parallel hybrid, which is this Boeing Sugar that we saw the video of earlier. And we actually are currently developing a megawatt inverter that could support that. And we have motors that are being developed as well at the megawatt scale. Remember what I said? I said earlier that the megawatt level is kind of that compromise between going to really large vehicles and really small vehicles. It's kind of the sweet spot where if you're developing technology there, it has spin-offs in these other areas. Okay, so also the ambient turboelectric. And if you notice, I'm using the word ambient, and then I've got last superconducting. All right, ambient just means we're operating at room temperature. We don't need to do anything special. Turboelectric means that we have a turbo generator, and again, we are developing megawatt inverters that can support that are at the efficiency and the weight that we need. We're also developing motors that can support that, both at NASA industry and with universities. And if you Google us in these different areas, you'll see there's a wide range of efforts underway. And then last but not least is the superconducting regime, in which you have the whole system at cryogenic superconducting temperatures, below 77 Kelvin. So at 77 Kelvin and lower, you can get situations where the resistance of the materials goes to near zero, which allows you to run a lot more power in a much smaller area. But there's things that need to be resolved, like AC losses. It turns out that even a superconductor, if you have a DC current on it, it might have near zero resistance, but if you have an AC current on it, it still has resistance. And so we're actually actively working that problem as well now. So the biggest payoffs are seen as maybe 30 or 40 years from now with superconducting, but if you want something in the 10 to 20 year time frame, the ambient technologies. So that's why there's a place for both of those approaches. Okay, so like I mentioned, 24 volts is seen as the ideal bus voltage. And you can see here that 200 kilograms cable weight when you're at 2.4 kilovolts and when you're using or at 2000 volts, 240 kilograms. You can see as you lower the voltage of the DC bus, that the cable weight increases, and that's just because the lower the voltage, the more current you have. The more current you have, the bigger your cables need to be. And it turns out for this star cable vehicle that a large percentage of the mass that we're adding to the vehicle is actually just in delivering the power from the turbo generators to the tail. Now, when you do your own trade studies with the on-demand mobility, you're going to probably have much smaller vehicles and less cable distribution and lower power levels. So something else is going to pop out at you, and whatever that something else is, that's what you got to tackle. So it's still going to be the case that if you can go to higher voltages and higher frequencies, everything gets lighter and smaller. So that tends to be the sweet spot for whatever you're working with, mechanical or electrical. Higher voltages and higher frequencies, you get a lot of benefits by doing that. Okay, so what does this mean in terms of system optimization? So for example, a typical conventional electric motor, if you look at the losses associated with it, the friction and windage, the core losses, armature, ohmic, stray loads, and so forth, stack up this way. Now, with a high temperature superconductor, the total efficiency is about 98.7% efficient, and you can see now that you have some losses that you didn't have before associated with the cryo, keeping things at cryogenic temperatures, but the overall system is better, and so that's the carrot. That's why we're pursuing that. And like I said, it's not out of the question to have superconducting UAVs, and it may in fact be especially if you use something like liquid hydrogen or liquid natural gas, that would be really interesting. You're still getting fluid density, and especially liquid hydrogen. That just produces water as a product, so it's also clean for the environment. But again, if you look at the system, if you look at the total system benefit, how do you produce hydrogen? Well, you typically have to use the grid, and if you look at the total cost of producing hydrogen today, then you don't get that same benefit. So that's why it's important to look at they say from well to wake. So from the very beginning, where are you getting your power from to the whole process of using it, and that's important so that you're getting a full benefit. Also. If you do go to cryogenics, then you can use a couple of different technologies, Stirling, Pulse Tube, and Brayton, to provide the cooling systems that you need, but those add weight. All right, and so for example, I'm showing over here, there's a sweet spot in this range for the operating temperature being about 55 Kelvin. If you use, depending on the technology that you're using, you're going to end up with different system masses. So if you try to lower the temperature, for example, that might make your electric motor lighter, but now your cryogenic system's heavier. So it really is, especially with flying vehicles, you can't ignore the system because you're adding weight somewhere, and you got to account for all of it, or else you can't fly it. Okay. So electric aircraft energy storage. If we could just have 100 times more energy storage available to us, it would make a lot of things easier. But it's not easy to do. And in fact, it's very challenging. And if you look at even the most optimistic projections for improving of this technology, maybe 2 times, maybe 3 times better, but it still doesn't get you to the Boeing 737 scale class of energy storage. And it makes sense when you think about jet fuel being 100 times more energy dense than batteries at this time, and that 50% of the mass of these large aircraft, 50% of the aircraft's weight is fuel. So it's massive amounts of energy, enough to power cities is what you're actually storing on these vehicles. So, but the good news is that for on-demand mobility applications, because if it's a smaller, shorter mission duration and lighter vehicles, then there's actually a chance to do this with this sort of technology. But in all cases, it breaks up into either some technologies are good at storing energy, some are good at storing power based on mass, and it's hard to get both. You like to be able to have enough energy and enough power. So that means, for example, if you have a 100-watt light bulb, okay, 100-watt light bulb, you might be able to have it on for 1 second if you use these dielectric, or if you use the batteries in this case, but it wouldn't last very long potentially. Okay, or the other way around. If you're not using a whole lot of power, but you can store a lot more energy. So, but you like to have both. You like to have high specific energy and high specific power. But so what people do instead is they do hybrid batteries and supercapacitors. So on your design challenge, I think you were told you can assume that you've got 2 or 4 times more capacity in both. Well, you can actually hybridize both and kind of get the benefits of both. And down here, you can see that roughly as the energy storage capacity of batteries goes from 250 watt hours per kilogram, that's good for about a 4-passenger vehicle. And as you get up to 750 watt hour per kilogram batteries, you're getting the ability to handle larger vehicles. But like I said, getting to that point is non-trivial. In all cases, you're adding mass, and you've got to manage that. Okay, well, not only does the energy storage add mass, but if you are producing power or cooling on your aircraft, you have a wide range of technologies. And these charts, even though they're kind of busy eye charts, they show all the technologies and where they fit on these curves. So if you have a particular specific power that's needed at a particular power level, then, for example, if you look in this chart over here, if you need 100 kilowatts and you need the highest specific power possible, then you might want to use a Rankine cycle or even a Brayton cycle. If you need 1 kilowatt to 10 kilowatts, you might use a Stirling is going to be your lightest option. And so you can kind of see that there's different technologies depending on what your vehicle's requirements are. Okay, and this is another way of looking at it over here, which is what temperature do you have available to work with as well, because that's going to determine the kind of materials and the cost of your vehicle. So when you look at the cost and so typically maybe 650 Celsius is kind of the trade-off point, right, where the materials get to be more expensive. So you can see if you're in that range, what sort of efficiencies you can expect and what different technologies would be useful in those ranges. Certainly Stirling and Brayton typically are kind of a winning option at these lower temperatures, and Rankine. And then also the whole cryo-cooler world of being able to use not just to produce the power, but now if you want to have superconducting available to you, then you've got a wide range depending on the temperature that you want to use. So if you're at 50 Kelvin, for example, then you're looking at maybe a turbo Brayton commercial unit being in this range here would be ideal. So you can refer to these charts based on the vehicle specifications that you come up with to what kind of technology is going to be optimal in those operating regimes. So you can see energy storage, power, and energy conversion all have a mass associated with them and an ideal operating range associated with them, including temperature, energy storage levels, power usage, and all of those features matter. So you can never just pick one technology and say that's it. And that's why people for all these years have been developing a wide range. The exciting thing about hybrid electric and the new area we're in now is that all of these technologies have a place because there's so many different uses for this technology. We haven't even talked about the military applications, but certainly the commercial transport, product delivery, UAV world, all of that technology, there's a wide range of options to look at. So this is a very specific electric machine development that we're doing. Like I said, we're developing 1 megawatt scale electric motors. They need to be at least 96% efficient. Specific power needs to be at least 8 horsepower per pound or 13 kilowatts per kilogram. That's roughly 3 to 4 times better than what you get today. And we're working with universities. We're also developing some in-house. And then our in-house version actually is interesting in that it's a hybrid motor in that we have a superconducting rotor only, but ambient temperature stator. And there's other groups too. If you, for your design challenge, look around, you'll see that Siemens, GE, a number of different organizations are being innovative at mixing superconducting with ambient and different ways of managing that. And again, it's all because having a net benefit it's like threading a needle. There's really a lot of technologies that need to all come together to make that work. And then also if you're going to have electric motors, then you need to have inverters and rectifiers that can convert your AC into DC. So we're also developing that. We're developing megawatt size inverters using silicon carbide and gallium nitride for the switching technology. There's also some cryogenic inverters that are being developed with Boeing. And I can report now that last year at this time, it was a dream that you could do this. Now, as of this past fall, the designs are closing, and we're actually showing that you can meet these very, very difficult key performance parameters. So it looks like that these technologies can be implemented and will be built over the next year and a half. So it's very exciting. The other challenge is thermal issues. I already mentioned that aircraft all have a mass associated with a mass penalty associated with them. Hybrid electric has mass penalties due to the energy storage, the power generation, the power distribution, the fault management components. All that has a mass, which if you don't have that managed properly and still maintain efficiency, it doesn't result in a net benefit to the vehicle. Well, the other part of all this is now you've got a thermal challenge that you didn't have before. You have components now that are distributed throughout the aircraft that are electric. Anything electric produces heat. Okay, there's nothing that's 100% efficient. So you have heat now, and the other challenge is that all of the modern aircraft today, military and commercial, are using composite airframe structures, and composites do not have very good thermal conductivity in the out plane. Which means you have these essentially large thermos bottles now that are collecting all this heat. So what are you going to do with all this heat? I'm going to show a couple of ideas. Your UAVs and on-demand mobility vehicles will also have thermal challenges. It's one thing to say, hey, we'll just put fins and manage it. But if you actually run all the numbers and the weight and the drag losses and so forth to have a closed system, you'll find it's not as easy as you might think. All right, so for example, with military and commercial aircraft today, you might use ram air, you might use convective skin cooling, you might dump some of the heat into fuel. Challenges with dumping it into fuel is that there's only so much fuel and it can only absorb so much heat, and we are approaching those limits now. There's also using lubricating oil. Again, that has limited capacity. Now you can use active cooling. So just like you use heat pumps or refrigeration for buildings and other places, but it typically will add weight to the vehicle or it will consume your engine power. So typically thermal challenges mean less performance, and it might even be so much less performance that it subtracted all the benefits of all the other technologies that you've developed. So it's a big deal. Phase change cooling is another thing. Again, that's basically you're melting a material, but you're storing the energy on the vehicle. But again, the challenge with that is it adds weight, and there's only so much heat that it can absorb. Heat pipes, pumped multi-phase, vapor compression, all of these things add weight and consume engine power. So for your design challenge, how are you going to manage your heat? Now, fortunately, your heat loads would be, probably less than what these larger vehicles are. But like I said, we're talking about potentially a megawatt of low-grade thermal heat. Low-grade means like 100 degrees C, 150 C. And it's low-grade because power electronics and motors and other components need to be at those lower temperatures. And when you're at low temperatures, it's hard to get rid of all that heat. All right, so this is actually a solution that I'm very familiar with because I invented this. We're going to be starting developing on this this year. This is just one idea, and I'm showing it to you so that you can think outside the box, and you can see that there are definitely new things that you can develop that not everything has been thought about at this point. What I'm going to show you right now is something that we were running into a roadblock, and we were very concerned. Well, we've got all these great technologies. Well, how do you close the system? So this is an example where what we do is this is star cable again. So it's that we have a turbofan generator on this side and a turbofan generator on this side. They're both producing thrust. They're delivering power to the rear tail cone thruster. But also what we're doing is there's waste heat coming out of the back of these turbofan engines. Roughly, turbofan engines are 50% efficient. On Earth, the power plants today can be like 65% efficient, 68%. They get that efficiency by using combined cycles. So rather than just using a Brayton cycle, they'll use a Brayton cycle followed by a Rankine cycle. Well, in aircraft, they haven't done that because the Rankine cycle adds a lot of weight. So you might get more efficiency, but the weight penalty was too much. So instead of doing that, what I'm proposing here is actually converting the energy, the 50% of the waste energy, into an acoustic energy. And that acoustic energy is delivered throughout the aircraft, and it drives a heat pump. And it raises the temperature from that low grade 100C to 600C, and then that energy gets returned back to the combustor. So I will show an example of this. So basically, this is an interesting technology. It's called thermoacoustics. And you put heat in, and this is the waste heat from the turbofan, and you reject heat out. And this is just the bypass air. And when you do that with no moving parts, it actually creates a sound wave. The sound wave can be very, very powerful, 170 dB, but you don't hear it. It's all in a tube. And the energy travels down the tube, all right? And when it runs into this another set of heat exchangers, it actually reverses the cycle, and you have a heat pump with no moving parts. And so you have 150 C temperature power electronics heat going to the cold heat exchanger, and we actually raise the temperature of that up to 600 C, and then return that back to the aircraft, to the combustion in the turbofan. And so here I'm showing kind of the complete cycle, what that looks like. If everything were perfect, you could actually get a 16% fuel savings while managing all of your heat. And the really great part about it is all of the heat goes out the back of your nozzle. So you don't have to have fins and heat exchangers throughout the aircraft and all that weight. So you actually get a net benefit in the performance of the aircraft and managing all your heat at the same time. So we're kind of excited by that. And I just wanted to kind of share that with you, that there's going to be many other areas where as you're looking at the vehicle systems and you get into a situation where hey, I'm just looking at this part of the problem, but I'm going to not look at these other parts yet, because you can only tackle so many things at once. But when you have to do like this design challenge and actually have to meet all those criteria and have it be commercially viable when you're done, you can see why only 1% of the technologies make it to the end, because there's just so many issues that have to be addressed. But I'm just pointing out to you that we do need innovation, and this exercise you're doing right now is very important to the future of developing these technologies. So we also have the ability to test these things. So there's a brand new facility that we've built. It's located in Plumbrook Station, which is part of our NASA Glenn Research Center. It's out in Sandusky, Ohio. And it's the first facility that can support full-scale Boeing 737 aircraft tests. And we've done some initial all-electric aircraft testing this year for the X-57, which is a battery-powered aircraft, which will be flown in 2018. But we also have the capability to test the full aircraft. So what I'm showing you here is this is still Stargable. So we have our tail cone thruster located back here, and we have our two turbo generators located here and here. And so you can see what our facility does is it captures the entire powertrain. So we don't have the fuselage or the cockpit. We don't need the cockpit, and we don't have the wingtips. But we can fit everything else in the building, and that's all we need to have in the building. But it's a 24 megawatt electric capable facility with 2 megawatts of thermal cooling, with altitude testing in the rear, so we can test our motors, power electronics, and other components at full altitude, which is typically 50,000 feet, but we're able to go to 120,000 feet. So, so when if you ever took to your design challenge and took it to the next step of building it, you'd have to have a way of testing it. And in the case of these really large aircraft, it required an entirely new kind of test bed. And so here's an example of the inside of that building where we have tested the EMI, the electromagnetic interference and radiation, from this just all battery, all electric aircraft. And it turns out that there's a set of standards that the FAA has. The FAA doesn't want you putting equipment on aircraft that's going to interfere with communications and other safety features. And so they have strict limits on what your EMI can be. Well, those standards were developed before we had very high power, very high voltage aircraft on the horizon. And it's kind of acknowledged that we need to revisit that. It turns out that the weight of your power electronics is very much dependent on the filters that are used, and those filter sizes are very much dependent on these EMI standards. The lower frequencies that are currently have strict limits on them in this range here actually are because of one heritage piece of equipment that's still on aircraft. And so, for example, so some of our industry partners are actively advocating for a change of those standards, and that'll help meet the future flight weight requirements we need. Same thing with your on-demand mobility design challenge. The FAA is going to have requirements that you're going to have to address, and they're very real requirements. So I've circled here the lower frequency range that are currently on the standards, and fortunately the standards for this all-electric aircraft, we were able to meet the DO 160G standards, which is FAA standards, and the military also has a whole other set of standards as well. And again, you can shield these things, but shielding adds mass to your vehicle. So it's a whole system challenge, and it requires improving all these technologies. In summary, there's key power, energy storage, and conversion technologies that are being developed that support both the on-demand mobility and the transport-class aircraft. This includes megawatt motors and inverters that can support electrified propulsion requirements, energy storage technology that can safely support on-demand mobility, and as you know, some of the lithium-ion batteries they've been having some issues with. There's a lot of energy stored in those batteries, and when the two chemicals, or when your barriers break down, you have issues. Energy conversion technology that can thermally recycle all the aircraft waste heat, and then there's also what this enables is heavier payloads. It reduces noise, can reduce emissions, and can also reduce the operational cost, which the Boeing 787 is already doing by using more electric components. It can create new mission capabilities, including duration and durability, and that's why your design challenging is possible and interesting. Is the hybrid electric regime makes it possible for the UAVs to have a future. And also the military is coming up with entirely new. If you Google lightning strike, for example, you'll find some public information about that, which is kind of a large-scale UAV. Also, some of the challenges that we have are you still have operational and regulatory changes that are required. Both, right now the FAA requires that you can see your UAV at all times, so there has to be a pilot that's watching where that is. So if you wanted to automate that, like Amazon and Google want to, you actually have to change the regulations. There's EMI standards and flight path management as well that have to be either adhered to or changed. And if you do change some of these things, then you have to look at the system effects of that. And then also the dispatchability and the infrastructure. I mentioned that the grid right now is 30% efficient. So if you're claiming that your energy storage system is some high efficiency, you're really not if you're using grid power. Now in the future that's certainly a goal, but again, if we want to make progress, it's a system solution. So you really got to look at the entire set of trade space. So in summary, the power technology is maturing at a very fast pace, and we've recently added turbo generation as well as boundary layer ingestion as some of the new areas where we're actually doing physical tests to confirm that the theories and the designs that we have are working. And with that, I think I'm available to answer some questions. All right. Feel free to send in some questions. This is live right now. I know when you have this much material, it can be challenging to where do you start with the questions. But one of the questions that I ask myself is let's talk about your design challenge. That's a very exciting area. There's a lot of new startups, a lot of new crowd-funded startups. Maybe after you do this design challenge, you'll find that you might want to form some teams and maybe try some crowdfunding and see if you can get a startup company going. There's a lot of opportunities, a lot of niche markets. If you can find something, for example, if you can make your UAV last more than 2 hours, that's important. If you can address the safety concerns of if you're flying 400 feet above people, what are you going to do if you have 1,000 of these in a neighborhood to ensure that nobody gets hurt? What is the ideal fuel or energy storage system to use? Liquid nitrogen is interesting because if you do crash, it instantly vaporizes and it floats. Liquid propane, not so good. It's heavy and will actually sink on the ground. If you're using batteries and supercapacitors, how much duration are you going to get? Those are all open research areas, and there's a number of startup companies that are interested in this. There's the big guys, Google and Amazon, have made a lot of press about this. There's also work over in Europe, Airbus and other organizations. They're equally as interested in hybrid electric, both for large-scale transportation as well as general aviation. So there's many opportunities. So as you're developing this technology and learning from this technology, you'll find that there's many opportunities to use what you learn. Okay.
Well, I'm sure you join me in sincerely thanking Dr. Dyson. He's provided a whole lot of information critically pertinent to what you're doing and direct application. So this will be archived. I hope you get a chance to revisit and listen to the taped message. But if you have any questions at all when we close today, please send those questions to the address that was at the bottom of your screen. That will be dlnwebcast@gmail.com. And we'll try to answer all those questions and actually post them at the website for the design as well. Okay, so again, thanks everybody who tuned in, both the students and faculty. And I also want you to join me in thanking Dr. Dyson for a very informative presentation today, critically relevant to what you're doing. All right, thanks very much for all of you for joining us, and also Dr. Dyson.
Okay.